Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2019 Physics Unit 2, Paper 2. Now, the first question is one from Module 1, and in Part I, it's asking us to define the term volt. So a volt is the unit of potential difference, right? It refers to the potential difference between 2 points in a circuit when work is done to move a unit of positive charge between the points. And so we can often represent that mathematically from a formula standpoint, right? We can represent the volt as being then equal to work over charge, right? So that's a volt and that's your potential difference. So that would be our volt, okay? It's a unit of potential difference. Okay, so now let's see what the next question is. For part 2, we're being asked to define the term Coulomb and state its relationship to the elementary physical unit of charge. So the Coulomb is the unit of electric charge. It is the quantity of charge that passes through any section of a conductor in 1 second when a current of 1 ampere is flowing. And so that would be 1 Coulomb, right? It's a quantity of charge. And so mathematically, from a formula standpoint, we can represent the charge as Q is equal to I times T. And the unit of this guy, which is electric charge, would be the Coulomb. Okay, so that's what the Coulomb is. And so we're being asked also to state the relationship of the Coulomb to the elementary physical unit of charge. And so the elementary charge, right, is often taken as a charge on a single electron, right? And the charge on a single electron is equivalent to 1.6 times 10 to the negative 19 Coulomb, okay? So that's how we relate the Coulomb to the elementary physical unit of charge. All right, and so let's move ahead now. So let's clear everything here. And now we're moving on to part B, part B. It says in the equation for Coulomb's law, F is equal to Q1 times Q2 divided by 4 pi epsilon naught R squared, right? That's the equation from Coulomb's law. They want us to state the meaning of each symbol and its corresponding SI unit, okay? So all these symbols, we have to say what they mean and what their units are, and so here it is. So the F is the force that is being felt between 2-point charges, right? So that's F. And it's a force, so it has units of Newton, or for short, N, right? Q1 and Q2. So Q1 is the charge on the first point charge, and that has unit of Coulomb, right? We said Coulomb is the unit of charge. And then Q2, this one would be the charge on the second point charge, and it's gonna have units of Coulomb as well. Then, what do we have here? We have R, right? Here's our R. R is the distance between the 2-point charges, and that's gonna have a unit of meter. That's the SI unit of distance. So it's meter, and its shortened form is just M. And then epsilon naught, now this guy right here is known as the permittivity of free space, and it has SI units of farad per meter, also written for short as F m to the minus 1, okay? So now we've accounted for every symbol here. Of course, you know pi is just 3.14, doesn't have a SI unit, so I don't think that's required here. All that's required is the F, the Q's, the epsilon naught, and the R. And so we've captured all of that, and so let's move ahead now. Okay, so we're at part C, and part C says positive 100 microcoulomb and a test charge of minus 5 microcoulombs are 3 millimeters apart. Calculate the force between them. Okay, so here it is now, guys, that we have 2 charges, right? So we can say perhaps that this is our Q1, this is our Q2, right? We have 2-point charges. And then we have a distance that separates them. So presumably that is our R. and they want us to find F, right? And so you see, based on the information that we're provided, it makes sense then for us to use Coulomb's law. So that's our strategy. Our strategy is to use Coulomb's law, that equation that we just explicitly spoke about a while ago. So we're gonna use that. So it's F is equal to Q1, Q2 over 4 pi epsilon naught r squared. So we're just gonna plug in everything that we have very carefully, right? Plug in all of these into this equation and we'll be good to go. Now, in your data booklet, there's a simplification here that you're gonna be provided, or that you'd always be provided, and that's to account for this here. So let me just kind of box this out as a simplification for this that you can get from your data booklet. So then what that means is that we can rewrite this formula here as 1 over 4 pi epsilon naught, right? And then we're gonna multiply by everything else. So it will be Q1, Q2 over r squared, right? And these are all the things that we're provided with in this question. But this part is a constant that you can find in your data booklet in the first page of your exam. And they are going to give you that value to be, let's write down that number. It is 9.0 times 10 to the 9, right? So already we have some values here that we can plug in, and that's mf to the -1. That's the unit there. All right, so now let's plug in the rest, right? These are question specific, so let's plug them in. So Q1 we said was 100 microcoulomb, so I'm gonna put 100 times 10 to the -6. Then my Q2 is this guy, so I'm gonna multiply by that. So that's gonna be 5 times 10 to the -6. That's a microcoulomb, right? And then now we're going to divide all of that side by the r squared, which is 3 millimeters. So I'm going to write that in meters as 3 times 10 to the -3. And that's going to be squared, right? It's r squared. All right, so when we work through and we simplify through, let's see what we're going to get here. We are going to get, just plug in that all into our calculator. Of course, it is suggested that you do it step by step, right? So let's just do it step by step. Let's break it down. I'm going to write back the first part for now, right? So let's just write that we don't have to trouble that part for now. So let's just leave that there. And let's break down this part. So when I break down this part, what will I have? I will have 500, right? When I multiply the whole numbers there, when I multiply these indices portion, I will get 10 to the -12 up top, and then on the bottom now, I would have had 3 squared would have been 9, and then 10 to the -3 squared would have been 10 to the -6. So then I can simplify further. I'm gonna keep my 9 right there. I'm not gonna lose it. Keep it there along with its units. And then this part, when I simplify, I'll bring the -6 up top, and then so I'll have 500 times 10 to, so I bring the -6 up top, it becomes +6. I'm gonna have 10 to the -6 up top. And then, of course, I'll still have my 9 down at the bottom now. I can take that 9 and go with that. And so now up top, what do I have left? I have 500 times 10 to the 3, right? I have my 10 to the 9 and my 6. I add them together. So I'm going to get 9 minus 6, just 3. And that's going to be in newtons. And so that's my force. That's my final answer. So this is my final answer here. Let me just box it. Let's just box that. So this is our final answer, right? So F is equal to 500 times 10 to the 3 newtons, okay? All right, so now we're done with part C, so let's move ahead. Okay, so now we're moving on to question 1, part D. So part D says that in the diagram shown in the figure below, so here's our figure, electrons are ejected from the lower plate of a parallel plate capacitor with a plate separation of 3 millimeters in a vacuum chamber. The ejected electrons have a range of energies and directions, right? So here's our parallel plate capacitor. We have a lower plate, positively charged plate, and we have an upper plate that's negatively charged. And so what we're saying is that the electrons are going to get ejected from down here, but in so doing, they're going to be ejected at a variety of angles, right? And so you can imagine that we have some that can just shoot up at a 90-degree. We can have some that shoot off at a particular angle, right? Varying angles, in fact, right? And so what we're saying is that there are going to be a variety of directions and a variety of energies that are associated with those electrons that are shooting off. Okay? So let's go ahead and see what the first part of this question is asking us. So here's the first part. It says, for those electrons which are ejected at right angles to the lower plate, so the ones that are just shooting up, so let's just drop those in. So an electron that's probably like just shooting up here, right? At a 90-degree angle, right angle to the lower plate. So for those ones, they want us to calculate the maximum initial energy in joules that they can have if none of them are able to reach the upper plate, which has a voltage of -3 volts with respect to the lower plate. So there's a lot to unpack here, right? So we're saying that electrons are going to get ejected at a right angle to the lower plate. So they're going to shoot up like this, right? And when they shoot up, let me just correct my arrows to be more accurate in terms of what's going on, right? When they shoot up at a right angle to the plate, they're not quite going to get all the way. They're going to get repelled back, right? Because they're negatively charged and they're coming up against a negatively charged. So they're going to like stop pretty much before they get there. And what the question is asking us is the maximum initial energy. So they want us to find an energy, right? They want us to find the max energy that they'll have initially if none of them are going to reach the plate, right? What else? The upper plate has a voltage of -3 volts with respect to the lower plate. So we can just write a -3 here and just say, let's take our positive plate as being at earth potential. So say that that has 0 volts, right? So then we can think about the field lines, what the field lines are going to run like this, right? The electric field lines. And so from a potential difference standpoint, right, our voltage will be equal to the final, right, the final destination, the voltage at the final destination minus the voltage initially. So that would be 0 volts. And so then the potential difference then between these two plates, V, will be so we're gonna do -3 minus the initial. So that would be, we can just say -3, right? So that is our voltage difference there, our potential difference. And so here we are now, we have to find initial energy, right? So we have a voltage, we have a separation, but we're not going to use the separation just yet. We have a voltage and we're asked to find energy, right? And remember, our species or our particles being ejected are electrons. So early in part 1, when we are talking about a definition for potential difference, right, which is this, we said that the potential difference, V, is going to be equal to the work done, right? Which can be used interchangeably as energy, right? Because the change in kinetic energy is the work done, right? And so if we're gonna find energy, we can say that the volt is equal to the work done over the charge, right? And we know this from part A. So we know what the voltage is. We already established it as -3. So we can put -3 here. We need to find work done, which is the same as our energy. So remember, we're using energy and work interchangeably here, and we can do that, right? And so the work is what we're trying to find, and the charge that's being moved is that we're moving electrons, and they have a charge of minus. We said this earlier, right, when we spoke about what the elemental charge is. So it's minus 1.6 times 10 to the negative 19 coulombs, right? So we have volts here and we have coulombs here. We're finding work. We're going to transpose to make W the subject. So W is going to then just be equal to us multiplying the 3 volts there times the negative 1.6 times 10 to the minus 19 coulombs, which is the charge on that electron, the electron that's being moved. And so W is then going to be equal to 4.8 times 10 to the minus 19 joules. Okay, so that is our maximum initial energy in joules that they can have if none of them are going to get to the top just before they get to the top, right? So this potential difference is still applicable of -3, and so that's what we used here. The charge of the electron is that, and so we plug that there, and we're able to find out that that's the work. So let me just box that real quick. This is our answer. We're locking in this answer. So that's our work, or the maximum initial energy that the particles can have, the electrons can have, okay? All right, so let's move on now to part 2 of this question, part 2 of part D, right? All right, so part 2 says determine the maximum initial velocity of the electrons in D part 1, right? And so here it is now. We just got an initial maximum initial energy or maximum initial work. And so if we just got that, what that means is, right, we know the formula for kinetic energy, or energy that we can use that relates it to velocity. And that would be that KE is equal to half mv squared. And so if we need to find the maximum initial energy, you know, it's going to correspond to the max, right? Let me just write that. It corresponds to the max energy, right? Corresponds to max initial energy, which is what we calculated earlier, max initial work, right? So let me just write that here. Remember, the velocity is correlated to the kinetic energy or the work. So if we're needing to find V, which is the velocity, we're going to rearrange this formula, making V the subject. So when we do that, what are we going to get? That the V is going to be equal to the square root of the kinetic energy times 2 over m, right? That's a mass. What is that mass? That mass is going to represent the mass of our electron, so mass of the electron. Very important to realize that, right? And so the velocity then is going to be equal to the square root of the maximum energy that we found earlier, which was 4.8 times 10 to the minus 19. We're going to multiply that by 2 and then divide it all by the mass of an electron, which we know is 9.11. Again, from your data booklet, the very front of this paper, you would go and you find the mass of an electron. It is 9.11 times 10 to the negative 31 kilograms, right? And so when you multiply everything through now, right? Multiply the top, divide it through by this, and then square root everything. We're going to come out with a velocity of 1.03 times 10 to the 6 meters per second. Okay, make sure your units are correct as well. It's a velocity, so it's going to have meters per second as its unit. So let's just box this in. This is our answer. This is the velocity. Okay, so remember now, the key to doing this question was to realize that there's a connection between the kinetic energy or the maximum work and the velocity as half mv squared. Okay, so this is our velocity here. So let's move ahead to part 3. All right. So part 3 says, calculate the acceleration of the electrons in D part 1. All right, so we're gradually ramping up, right? We're ramping up. The question is ramping up as we go along. So now we're being asked to find acceleration, right? So we know that fundamentally, right, based from Newton's laws of motion, we know how force is related to acceleration. So we can start there, right? We can say that F is equal to mass times acceleration. So if we need to find acceleration, we can rearrange that formula, and it's going to be A is equal to F over M. All right, so here's the thing now. Force, we need to know what force is, right? So what we can do at this point is we know from our work that the electric field strength E is equal to, what is the electric field strength? That is equal to F over Q, right? And so F is equal to the electric field strength times Q, right? We also know that the electric field strength can be represented as the voltage over the distance between the plates. So we can just do that substitution, put back our Q, and then voila, we have a formula for F. So F is equal to V over D times Q. So let's just plug that in here now, right? A is equal to force over M. So force, we said, is V over D times Q. And then, of course, we're going to have to divide by M. So that's times 1 over M. Right? So now we're ready. We're ready to solve this. We can plug in everything now. And remember that this M is the mass of an electron. Mass of an electron is the electrons that are being accelerated, right? So let's plug in everything. Right? So now we know the V from before to be -3, right? We calculated that potential difference in an earlier part of this question. So we know that that's still true. Our Q is still minus 1.6 times 10 to the minus 19. That is the charge of an electron. The distance, we know, they told us is 3 millimeters. So we're going to put 3 times 10 to the minus 3 there. And then what else? We're going to multiply now by 1 over the mass of an electron, which is 9.11 times 10 to the negative 31. Right? When we put all of this together, we're going to come up with an acceleration of 1.75 times 10 to the 14 meters per second squared. Remember now, that's our unit of acceleration. We have to put the right units. So let's just box this. That's our answer. So that's acceleration. Okay? All right. So the key here is to go back to basics. F is equal to ma, right? But for this particular question, we weren't given a value for force, but we know that force is equal to V over D times Q, right? We can use that to substitute in for force, and that's exactly what we did here. And then we had the mass of our electron there, and so when we plug in all that we knew, all that we were given or we were able to calculate, then we come up with the acceleration that's needed here. 1.75 times 10 to the 14 meters per second squared. All right, so let's go ahead now. Let's clear this and we'll move on to 1E. Okay, so one part E says the graph below shows the trajectory of one electron, just a single electron, which is ejected at an angle theta to the lower plate. Each large square with bold borders has a side of 0.5 millimeters, right? So here is the trajectory of one electron that's at an angle. It's like coming out like this, right? So the electron is shooting out like that, right? At an angle theta here, right? At an angle theta to the lower plate. So the electron is shooting off like that, all right? And they're saying that that border there, right, has a width of 0.5 millimeter and also down here. 0.5 millimeters. So that's good information for us to have, okay? All right, so let's go ahead and see what the first part of this question is asking. It says to draw a tangent to the curve in the figure, right? And measure the angle of ejection. All right. So drawing a tangent is just drawing a straight line to the curve. They didn't say explicitly to which point on the curve, so we can just draw a straight line that touches any point that we want on the curve. So I'm gonna go ahead and draw my tangent. That's a tangent there that we're drawing, just a straight line that touches some part of that curve there. So that's a tangent, and they want us to measure the angle of ejection, right? So I drew my tangent to like the initial parts of the curve because I knew we're gonna be asked to measure the angle of ejection, right? And the angle of ejection we said earlier would have been this angle right here, right? Is the angle at which that electron is shooting off from there. So we could just put theta there. So that's what we're being asked to measure. No, in the exam, you would take your protractor and measure that angle, right? You just place your protractor on the graph and measure that angle there using your protractor, right? And so because I don't have a protractor right now, I'm doing this on the computer. What I could do is I could just do a tan theta, right? To get what my angle should be. So I'm gonna like just mark out these points here. And they already told us that this is 0.5 millimeters, right? And so if I take this here as my opposite over my adjacent, so I'm just gonna write that. I'm gonna write what I'm doing over here. I'm just using tan theta to just roughly approximate it by calculation because I don't have a protractor to measure it. You would do that in your exam. But I'm gonna just say, okay, tan theta is gonna be equal to my opposite over my adjacent, right? We know that from our trigonometry. My opposite in this case is gonna be a value of, that's roughly, so each of these little tiny lines is 0.1. So that's 0.1, 0.2. So that's about 0.2, I'm gonna say about 0.28, right? So that's about 0.28 for my opposite. So that's 0.28 over my adjacent, which is 0.5. So my theta is gonna be the inverse tangent of that whole thing. So that's the inverse tangent of, let's do that real quick. So when I work that through, I get a value of theta for about 29.2 degrees, right? So when you measure that with your protractor, hopefully you come out with a value like that. All right, so we're gonna work with this for our theta. So let me just box that real quick as we've been doing. It's good practice to box your answer so there's no confusion as to what you're submitting to the examiner as your final answer. So here I'm saying my theta is 29.2. So let's go ahead to see what else is being asked of us now. So in the other part now, let's see. Right, we're being asked to read off the maximum height reached from the lower plate. So how far is the electron gonna shoot up, right? The maximum height. So it's in this y direction here, okay? So let's do that real quick. This is just manipulating the graph and the scales that they told us. So this is the maximum point. Well, the maximum point is actually, let's see. It starts going back down over there. So our maximum point, this looks like the top. That looks like our maximum point. So what we need to do then is just like meet our y-axis and see what that correlates to. So let me just draw a line here so we're as accurate as we can possibly be. So here's my line that represents my maximum height. So this is my maximum height, right? From the lower plate up there. So that's my max height. So that's my height max. I'm just gonna say H max. I'm gonna call it H max, right? So each of these squares, remember, is 0.5 millimeters. So two of them will be 1 millimeters. And then each of these little lines is 0.1. So that's what? 0.1, 0.2, 0.25. So that's 1.25. Okay, so my H max is 1.25. So H max, the maximum height that the electron is going to reach from the lower plate when it gets shooted off at this angle is going to be 1.25 millimeters. Okay, so that's our answer there. We're locking in 1.25 millimeters. And then we're ready to move on. So that's our H max. Okay, so moving right along now to part 3, which is part 3 here now. So part 3 says, read off the distance traveled parallel to the plate before being reabsorbed. So it leaves the plate down here. So let's just mark this as our initial distance. So it's leaving down here. So let's call that 0, right? It's moving from here. It's going. It reaches a peak up here. Then it starts coming back down. So just before it hits here, just before it gets back down to the plate, we are going to read off that distance. So we're reading from 0 to out here. Every square, right? Every one of these squares is 0.5 millimeters, they told us. So how many squares do we travel through? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we travel through 13 of those squares. So what is that? That would be 13 times 0.5. So this would be 6.5 up to this point. And then all of these little lines are 0.1. So 6.6, 6.7, 6.8, 6.9, right? So that's 6.9 right there. So the distance traveled parallel to the plate before being reabsorbed is 6.9 millimeters. So just gonna write that here. Distance traveled is 6.9 millimeters, and we're just gonna lock that in. Right, that's our answer, and that's how we achieved it, right? And so with that, we've come to the end of this question. So definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right, you'll see our Module 1 playlist, where you'll find tons more interesting content that will be helpful in getting you prepared for your exam. Okay? Thanks for watching, and we'll see you in our next video.